Yeah, so make sure you're doing your homework and your Chapter 6 and 7 quiz due Thursday at 6 p.m. Any issues with that, let me know. We did write down last time the content of the exam, and I guess today we can discuss any problems you'll have or y'all want to look at. Does anyone have any homework questions, quiz questions, exam review questions?
I had a question for homework. I believe it was 6-3. It had to do with, it might have been the third one? Or no, seventh one, sorry.
This one?
Yes, that's the one.
Okay. Region bound by the curves, find the volume revolved around the y-axis. So, maybe you remember what inverse sine looks like, maybe not. The ones on, like I said, the ones on the exam will have an accompanying graph for that. So let's go ahead and graph this. X equals 0, y equals pi over 4.
I'm so sorry.
You are good.
I don't know what happened. Just the pressure or something.
Okay, so it doesn't specify what method to use. So then you've got two methods. It's really up to you to determine which method makes more sense and/or which method yields something you can integrate at this point. So if we're going to find the volume revolved around the y-axis, revolve around this axis. Do we want to do parallel to the axis of revolution, which would give us a shell, or do we want to do our rectangles perpendicular?
Perpendicular seems easier to me.
Perpendicular seems easier. So if we go perpendicular, let me erase this. So perpendicular to the axis of revolution, this is one of our rectangles. Okay, so the volume perpendicular to the axis of revolution, what's that going to generate? What kind of figure do we generate that we're finding the area of? A disk, right? It's a circular disk. So this is going to be the disk method. Our rectangle's thickness dy. So we're going to integrate with respect to y using the disk. Here it's just pi r squared. There's no gap between the region and the axis of revolution. Okay. So we need the r in terms of y. Radius, right minus left. So we have the right function. But we want that in terms of y, not in terms of x. So we've got to solve for x. Everybody agree? Which is why this method's easier, because otherwise you're going to have to integrate some form involving inverse sine. Okay, so we solve for x. What do we have? Sine of y, 19 sine y. So that's what our right function is. Our left function, of course, is 0. Okay, so a radius 19 sine y. Our volume is given by pi r squared times the thickness. So we'll say volume is the integral pi times r squared dy. And y ranges, our rectangles range from where to where?
0.
Yeah, 0 to the blue line, pi over 4. Is everybody okay with the setup there? Okay. Go down here. What's, anybody know what 19 squared is?
I think it's 364.
364?
What, 361?
361. So we have to integrate 19 squared sine squared. If everybody remembers how to do that, super common integral. You can either remember the identity to transform it, or you can just remember the overall result. I don't really care. But we're going to use the identities 1/2, 1 minus cosine of 2y to integrate that. So I'll just do it over here to save some space. We have 1/2 y minus antiderivative of cosine of 2y is
2 sine 2.
sine 2y. That's the derivative,
Oh,
kind of.
divided by 2?
Yeah, divided by 2. Yeah, so we divide by 2 minus sine 2y over 4. Sine of 2. Okay, so that's the antiderivative of sine squared. So again, if you want to remember just what we have here as our last step, that's fine.
Which trig identities do we have to know for the test?
I would know the common ones: Pythagorean identities, the double angle, and sine squared, cosine squared.
Okay.
Yeah. Those are by far the most common ones throughout the semester. Or, you know, if you wanted to leave the 1/2 out, it's just going to be this constant here anyways, so. Yeah, whatever you want to label the antiderivative as, but that's, I don't know that this will divide evenly. We'll put the 1/2 out with the other constant. From 0 to Any questions about that? Does that make sense? So you could probably finish it from there. It's not that we couldn't have done this one using the shell method. It's just the integration would have been less deadly, I think. You want to be familiar with both ways, though. Because on the exam, it'll be some regions, and it'll say use the disk method, use the shell method, use the washer method, or whatever. So you want to be familiar with both. Is that all right? Did that answer your question? All right. What else?
For 6.6, number 2.
Find the area of the surface revolving x cubed from 0 to 1 about the x-axis surface area. So you've got to remember the formula for the surface area. Surface area was given by what?
Square root.
Square root.
Derivative of f of x plus
What's one?
derivative of x squared plus
Okay.
squared.
Yeah.
It should be,
What else?
it should be anterior video.
Yeah. So we had a 2 pi. And our differential dx. And this was the surface area revolved around the x-axis. Similar situation for the y-axis, but with surface area, the axis of revolution is the variable that you integrate with respect to. Okay. So we've got to find f prime squared plus 1. Or y prime squared plus 1. So y prime squared plus 1. I don't really have a preference how you should write these steps out. Really, all I'm looking for is like this part right here, the integral part. So, okay, so that's going under the radical. We still have our 2 pi. The integral from 0 to 1 is given. Function times the square root of this stuff. Okay. So what's it do from here?
Call u equal like 9, like x over 4
Uh-huh.
over 1.
So u substitution. Again, the function under the radical has a constant times its derivative right here. So that's always a u substitution. Okay, take the derivative of your substitution. dx. And we just want the x cubed dx for here. So we've got du over 36 is x cubed dx. Is that all right with everyone? Any questions? I've had some questions about emails about your substitution, so I was just going to make sure everybody's cool with that. All right. So what do we get? Part of 2 pi over our 36, our integral. That's our x cubed dx is our du. And the square root of u here. And yeah, I never know what people prefer. Do y'all prefer, just show of hands, who prefers to do the substitution with the u and change the bounds with u and stick with that? Who does that? Who plugs back in for x to use the original bounds? Okay, so we got a decent mix here. Either way, we go about this. When x is 0, we're going to u equals 9x to the 4th plus 1. So when x is 0, u is 1. And when x is 1, u is 10. So the bounds look easier with x. The function is a little bit simpler with u. So it's, kind of a toss-up. Okay. So we've got u to the 1/2, u to the 3/2 times 2/3 for our antiderivative, 1 to 10. We have 1, 8. So I guess we'll call this 18 pi. Simplify that 6 pops at 18 divided by 3 times 2. 6 times 2 is 12 pi. And then we'll just evaluate the u to the 3/2 from 1 to 10. Okay. That's pretty much it. Any questions? Did you get stuck somewhere?
Like evaluating it, my MATLAB wanted
The exact answer?
the square root, yeah, and I couldn't figure out how to do it, I guess.
Okay, so we have this. We've got 10 to the 3/2 minus 1. So I wouldn't take that.
I don't think so.
Okay.
You did the root, how did you make the?
So this is the cube root, remember? Or sorry, the square root of something cubed is this right here. So we have 2 of those, we can take it out. Yeah, 10 root 10.
Yeah, I wrote down my answers, so that's what they did.
That's what they did?
Yeah.
Yeah. I don't know, I'm not really that picky. If you left it like this right here, it's totally fine. So,
Can you draw up a little bit?
more?
Yes.
So I have a question from the quiz. Should I email it to you or can I just read it off?
Yeah, we can look at it now.
Okay.
So why do we have 2 over 36 and we have it should be the 1 over 18? 2.
Oh, did I write that
18
wrong?
pi.
Ooh, you're right. Yeah, I messed that up. So this constant would be different here. Thank you. What do we have? that, and 1 over 9, 1 over, sorry, this pi
187.
should not be there. Pi's up here. So we got 1 over 27 pi, pi over 27. Is that right? What's this? Thanks. I'll fix it here too. So quiz. Which one?
Number 7.
So the arc length on one from 127. Arc length, capital L. What was the formula for that one?
Probably square plus 1. Anti-torsion of that. Or the dx.
Yeah, dx. Is that right? Yeah, that's it. All right, so let's find the derivative of y. Y prime. So what's y prime?
Is the x over
It's over 2/3.
X to the 2/3 minus
minus
X to the negative
quarter
2/3 over 4.
x
x to the negative 2/3 over 4. What do y'all think? Okay, there's y prime. Y prime squared. So let's just write this out. We've got to square that. I know it may seem like a trivial thing, but don't just square the terms, right? You got twice the product of the cross, twice the product of the two terms. So you can't square the first two, you just got to remember 2 times the product. So x to the 2/3 squared would be what? Right, we square them, 4/3. And then we have our negative 1/4 squared. And x to the negative 2/3 squared. And then we multiply these two things together, we've got a negative 1/4, x to the 0, right? So negative 1/4, just write it as that. Twice negative 1/4 gives us negative 1/2. Okay, and then we're going to add 1. When we add 1 here, get x to the 4/3 plus a half plus 16 x to the negative 4/3. So keeping in mind that that expression has to go under the radical, these are either the radical goes away because you have a quantity squared, or it's going to be a u substitution. So how does the y prime squared plus 1 factor?
Just GS, to the plus.
Right, right. So the middle term's different. 2 times a times b, this is negative 2 times a times b. So this factors as the same thing we had before we expanded. With a plus there instead. Any questions on what we've done? So then that goes under the radical for the arc length. 1 to 27. So then we're just integrating powers of x. So they want an exact answer too, so it's kind of the same idea. You're going to have the fifth root, or sorry, the cube root of something to the fifth here. It's kind of the same principle for the 3/2 power. All right. Any questions on that? So you've got to remember these, any of the formulas that we've used, you've got to remember them for the test. So the only exam is where we can use a note card is the final. So like all formulas and stuff have to be remembered going into the exams. All right. Any other questions on that?
For the 1/2, where did the x's go?
Do what? The 1/2? The positive one?
For both of them, I guess, because
Where do they come from?
But when you multiply it out, does it both terms have x's? So what did that happen?
Yes, but it's this here. It's x to the 2/3, if you will, times the x to the negative 2/3.
Oh, I see.
So you have to add those, and then you get x to the 0, which is 1. So that's why there is no x there. Yeah. All right. No other questions you'll have?
I had one at 6.2.
Okay, 6.2. dashed curve, determine the area of the shaded region. We can do the whole thing, or we can utilize symmetry. So we're gonna have our rectangles running that way. The area then is the top function minus the bottom times the thickness. So with respect to x, the area top minus the bottom. Does that look all right? Minus the bottom. We can integrate both of these. Again, cosine squared, we would just use the identity. And secant squared is an unknown antiderivative. Or do we need to do something fancy there? Yeah, derivative of tangent is secant squared, antiderivative of secant squared is tangent. Okay. So those shouldn't be terribly difficult to find the antiderivative of. It's kind of tedious, I guess. What are the bounds? Figure out where these intersect. And so honestly, you can use symmetry like whatever. If this is pi, then this intersection's over here is negative pi. So we can use symmetry to do that. Or we can just say, I'm just gonna go from 0. I'm just gonna go from 0 to this point right here, and then double that. So however you like. I'm going to go from 0 to that point of intersection and double this. But we do need to find this point. So we have to know where these two things are the same. Any ideas? Multiply by 4. Okay, where does 16 cosine squared equals secant squared?
We could use that. Is it 1 minus tangent squared is equal to secant squared?
Yeah, 1 plus tangent squared or secant squared. Yeah,
And then you can turn tangent to cosine, so
cosine over sine. Then we would have like cosine and sine floating around.
Just say 1 over cosine squared.
Yeah, I think that's the best route. That way we just have, it's kind of the same function, but what that gives us is this. So I guess there's a few ways to think about it from here, but now we only have one trig function to worry about. So we could, I don't know, you could divide 3 by 16 and take the 4th root of both sides, get positive, negative, whatever. We could rewrite this as one thing. And then factor that as a difference of squares. Either way, just dividing and taking the fourth root or factoring it, you get the same result. So we have two options here. Or when does cosine squared equal to 1/4? So cosine squared x equal negative 1/4. Is that something we can solve?
Square root.
Square root it, yeah, and then what happens? Square root of a negative. Yeah, just, look at it like this. This is cosine quantity squared. If I square anything, it's never negative. So that doesn't contribute to anything. It's this one that contributes. So we have when does cosine equal plus or minus 1/2?
Square root 2 over 2.
When x is, sorry,
Square root of 2 over 2. I believe.
square root of 2 over 2? Or that's 1 over root 2? What do y'all think?
I think it's pi over 3, but I don't know.
Yeah, cosine of what is 1/2? It's gotta be a radian, right? Plus minus. You're really solving two equations, but you're gonna, I guess, use symmetry is what I would do. I wouldn't worry. I would just find one and then use the other one. So when does cosine x equal to 1/2, or when does cosine x equal to here when x is pi over 3. So that's really all we need. Cosine of the negative of that would be negative 1/2. So this would be pi over 3 here. This is pi over 3. This is negative pi over 3. We'll just do that one. That's the setup. Anyone have questions on that? Sure.
So on the test, do we need a calculator or not?
I don't think you absolutely need one.
Okay. So if we get a question with like sine and cosine, we should have the unit circle memorized pretty well, then, right?
Yeah,
Okay.
I would think so. Yeah, unless you have a calculator, I would hope that you all just knew those values. But yeah. I mean, I would recommend a calculator, just so you, like, if you finish, you can go back and check your work. It's always a good thing to do. Everybody makes mistakes when they're in a rush. Okay, all right. Any other questions about this?
So the derivative, antiderivative of secant squared x over 4, would it just be tangent x over 4?
Right. Yeah, because that 1/4 is a constant, right? If it's secant squared 4x, then it's tangent 4x over 16. No, this is what we're gonna use to find the antiderivative of cosine squared.
Oh, it's just the line.
Yeah, so we're gonna do this, think about it this way instead.
But you could simplify that forward with the half or whatever.
Yeah, this 4 could come out, so you'd have 8 here and just integrate cosine squared. Does that make sense?
Would the 4 come out even though it's subtracting the?
Because you can separate them.
Yeah, you can separate them, so let's go down here.
You mean separate like the integral?
Yeah, split it up.
Yeah.
So we're just gonna go ahead and write this out like this. Cosine squared as 1/2 1 plus cosine 2 x. We'll just write cosine squared like that. Minus, we'll just leave this one. So we're, that was secant. 4. So then, yeah, we would break it up. This 2 times this 2 would have 4. I mean, I guess you don't have to break it up really, but this first one, and then for the second one, we got a half. So I would take this 1/2 out in front. It's minus 1/2. Secant squared. Yeah, same balance here. So that's kind of what it would look like. Does that help?
Is the 1/2 multiplying, or is that 4 multiplying on
This one? The 4 out in front of the cosine squared? Or
Yeah,
this?
why is it 1/2, like minus 1/2, not the 1/4?
Oh, on the secant squared?
Yes.
Because this 2 right here, this 2 times this right here comes up here. Or you could just leave the 2 out and then mess with all of this stuff and then multiply everything by 2. Because I don't know how everybody does this. Some people like just always take the constants out no matter what they are, and some people just continue to leave them in. I'm inclined to take them out as I see them, but other people don't do that. Okay. Any other questions about this one? All right. What else do you want to look at?
Can we do some volume by slicing stuff?
Volume by slicing, any like,
All the
particular thing?
particular one.
Or just all of it?
Just like a random one, just like you would probably put on a test.
That I would probably put on a test?
Maybe.
That's on the test.
I'll give you a, I don't know if we did some of these already or not. Some of them we did. Let's go for it. Let's look at a few of these, a few methods. So we're gonna let R, capital R, be the region bound by y equals to x. Y equals x to the 1/3. 1. And we want to find the volume when R is, let's see, revolved around the x-axis. So we've got capital R revolving around the x-axis. So I guess we can look at this, let's see. Let's look at this a couple of ways. Part A, I guess we'll call it Part A. Use disk washer.
Oh, is that still? I meant like ones with like cross sections that are like different shapes.
Oh yeah, those aren't on the exam.
Oh. Sick.
So you want to scrap this?
If everyone else wants to see it, I'm cool with it.
So yeah, the ones where it's like the general slicing method to find the volume, like you've got a, you got two parabolas intersecting and the cross sections are equilateral triangles. Those kinds of questions won't be on there. So yeah, my bad, I misunderstood. Shoot, you want to keep going with these?
I had a question. So for this problem, it's kind of related, but how would you do it if the axis from revolving around is above where the intersection of the graphs are?
So like if we revolved around like y equals
y equals 2 or something.
2, yeah.
How would you-
So maybe we can look at that next. So like if we revolved it around this line right here.
Yeah.
Yeah, it's still the disk
Okay.
idea,
I'm just
and then
confused,
top minus
like,
bottom for
with
outer.
respect to what? Because it's kind of like flipping around the place you're rotating it from, which just kind of confuses me. So.
What do you mean? Like,
You're normally rotating it below the graph, but in this case, the upper function would be the other function. because
Right.
it's below the axis that you're rotating around.
right?
So.
Yeah, that's the only modification we would need.
Okay.
Because remember the outer radius with the washer method, the outer radius is the function that's furthest from the axis of revolution.
Yes.
So if we revolved it around this line, then we would have the outer radius being the distance from the axis of revolution to the function itself. Or, whatever, that's 2 minus x.
So when you rotate it around the graph, or the axis you're revolving it around, when you put it on the other side of the equation, that would basically multiply it by a negative. So it's below the graph, so I'm trying to explain what I'm thinking. Yeah, because so the function that was on bottom is now on top with respect to the new axis that you're revolving it around.
Yeah.
So you would basically multiply the whole equation by a negative so that bottom function would be in front of the other one. So you're subtracting the upper function there from the lower function because the axis is above the intersection of those two functions.
Mm-hmm.
Okay. Is there any other change you would have to make?
No.
Okay.
No, well, we'll maybe like with these two different methods, then we'll look at it like this.
Okay.
Yeah, so we'll consider that in a moment. Definitely worthwhile to consider rotating it around other axes, like x equals 5, y equals 2, you know, those things we should know how to do as well. All right. So we're rotating it around the x-axis, and we're using a disc or a washer. So when we cut into this, which way do we have to cut into it? Up and down or left and right? Up and down, right? Disc washers are always perpendicular to the axis of revolution. Okay, so then we say, all right, well, so if I'm doing that, I need to integrate with respect to x. I can't stress the importance of that. Like a lot of these problems, people will simply miss because they're integrating with respect to the wrong variable. It's not that they had something set up incorrectly, it's just that you were integrating completely with respect to the wrong variable, so it's like totally wrong. So draw a picture, even if it's just a quick sketch, and say, all right, well, I'm parallel to my axis of revolution, I have a thickness dx, and go from there. Super important. Okay, so we've got distance between, or a gap in between the region. Here's our region. And the axis of revolution, so we're actually going to be using this. So remember that's pi times the outer radius or larger radius squared minus pi times the smaller radius squared. Another problem I see when doing the washer method is people just want to do the outer radius minus the inner radius and square all of it, but it's each individual radius squared. So also super important. Okay, so we have pi times the integral. The distance from here to here, that's our outer radius, or larger radius, capital R. And the distance from here to here is our little r. Okay, so we have pi times our outer radius squared. Again, we're just measuring that distance. It's the top thing minus the bottom thing. So we have x cubed, sorry, the cube root of x, rather, minus 0. So there's capital R, we want to square that, minus lowercase r squared, which is just x squared. Top minus bottom again.
So if it were a different axis, like y equals 2, would the 2 be squared as well inside?
Inside?
Yeah, so you said like so if it were revolving around y equals 2, would it be x to the 1/3 minus 2 squared?
It would be 2 minus x to the 1/3 quantity squared, right?
Okay.
Yeah. So it's always that distance top minus bottom quantity squared, or left minus right squared
Okay.
quantity squared when we're doing the washer method or the disc method. Okay. And our bounds are from 0 to something. So where does x equal x to the 1/3? Not 1, I think that's kind of obvious or trivial. Okay, that's the setup. Any questions on the setup? Well, all right, then in part B, we'll find the volume using shells. Same region. Still revolved around the x-axis. We're going to use cylindrical shells. We need to have our slices or our cross sections parallel to the axis of revolution. So those are our cross sections filling up our regions. So the formula for the shells was what? 2 pi times r times h. All we're concerned with is the area of the cross sections. 2 times pi times r times h. So this distance that the cross section is marked out right here, from here to here, what is that? Is it 2 times pi times r times h? Which one of those is it? What is it?
It's
H, right? It's the height of each. It's always the case when you use shells. The length of your cross sections will always be the height of the shell. What's the radius? Some y value, right? The distance from your cross sections, all of your cross sections, we've just drawn one here, but the distance from your cross section to your axis of revolution in the shell method will always be your r. Okay, so we had to slice horizontally. That means we have to integrate with respect to y. So if you did, 2 pi times the radius in terms of x times the height in terms of x, that, you're just going to miss that problem. It's super crucial to set this up correctly. Okay, so we have, let's do it over here, volume, that's 2 pi times the integral with respect to y. The h, well, we already said what r was. R was just some distance y, right? Some y value minus 0. 2 pi times r. What is h?
right minus left.
Right minus left, which is
Y minus y third.
right. Right minus left is the height. And y ranges from 0 to where? Also 1, yeah. To right there. So that's the setup for the shell method. Questions on either one of those? So part C will say same region. Capital R. Find the volume. When R is revolved. About, what do we want to do? Let's say y equals -2. So we'll maybe look at this, and when we revolve it around, like y equals to +2 as well.
Do you care what method?
Yeah, so like we should probably parse this up into looking at it from disc washers and shells. So like looking at both of them, I think, is what we should do. But we'll take a break for right now, and then we'll look at this with disc washers and shells. All right. what were we gonna do? Oh yeah, we were gonna do, I don't know, let's call it part one. So we'll use the disc or the washer. So we're revolving our region now R around this axis. Y equals -2. So we want to use disc washer, it specifies that. So again, our rectangles or our cross sections are running perpendicular to that axis. We're integrating this with respect to x. So we have to do the pi times outer radius squared minus the inner radius squared. So the function furthest from the axis of revolution here, that distance is your capital R, outer radius. From this function to the axis is your lowercase r. So we'll have our volume as pi, integral from 0 to 1, same bound, same region. Capital R squared minus lowercase r squared with respect to x. So what is our capital R?
Capital low G.
Right. So that distance, top minus bottom, x to the 1/3 minus -2. So that's x to the 1/3 plus 2. Top minus bottom. Similar thing with the smaller radius, lowercase r is x minus a -2 or x plus 2. So that's our volume set up there. Yeah.
Hey, for any reason, do we have like the same question with this one, but doesn't call for any like the methods?
Yeah, I mean, if it doesn't specify a method, you can use whichever one you want.
Okay.
Yeah.
I thought we have to do both.
Yeah, we'll do both. But if it said the same region, find the volume when r is revolved around the line y equals -2, and that's all it said. You can choose which one you want to use, disk or shell. Yeah. But if it specifies, then of course do what's specified. Yeah. So this would be a little bit tedious because you've got to expand these, and you've got what, 3 terms here, maybe 4 and 4 here. So you're integrating powers of x, but there's many terms once you expand that out. Does that make sense? All right, so that's washers. Part 2, we'll say use the shell method. In the same region. The shell method formula changes, the setup kind of changes. Shells are parallel to the axis of revolution. We're integrating then with respect to y. And again, the length of your rectangles for the shell method is always the height of the shells. The radius is different here because the radius, again, distance from your rectangle to the axis of revolution. Okay, so then the volume's going to look like 2 pi times the integral r. What is our radius here?
Y plus 2.
Y plus 2, do y'all agree? Y plus 2 is the radius. Again, that's just the top minus the bottom. This value here at the top is just some y value. Okay, 2 pi r h, again, right minus left. So I think we did that earlier. Was this. So really, if we're rotating this around a different axis with using a shell method, the radius is the only thing that's going to change. And then bounds are the same. It's the same region, 0 to 1. Okay. Questions on that? So again, we have to multiply this out. We can't integrate across a product like that. Okay, so don't split this up into 2 different integral products. It doesn't work that way. All right. So, notice like if we rotate this around the line the region around y equals -2, you get a particular solid. So you get the same solid if the region were down here and we revolved it above like that. You get the same exact figure, but the setup does change a little bit. I think I'll start a new page. So we'll call this part D. Setup does change a little bit. Same region, capital R, and we want to find the volume. When R is revolved about y equals to 2. Oops. So I guess we'll Disc-Washer method here, revolved around this axis, perpendicular. Our rectangles are perpendicular to the axis of revolution. From the axis of revolution down here, what would that be? R, capital R, lowercase r? Lowercase? Capital R, right? It's the outer radius. It's the larger radius. So we're revolving this around here. That boundary is going to be like this, right? So we'll have this kind of thing. So that's going to be the outside of the figure, the outer radius. So that's capital R. And then this is now lowercase r, or the inner radius. Does that make sense? Okay, find them the same way still though. Capital R, top minus bottom. Lowercase r, top minus bottom. So this capital R now is 2 minus this function, which was x. And the lowercase, or sorry, the small r inner radius would be 2 minus x to the 1/3. Which will specify this is the washer method. So the thing that changes here, we've got pi times r squared minus lowercase r squared. Does anyone have questions on this? What would be different if we used the shell method from what we had previous? With the shell method, only one thing changes. Oh, sorry, still the same bounds. So shells parallel to the axis of revolution, thickness in the y direction, dy. This right here, again, it's always the height of the shell. So the height of the shell didn't change.
Radius.
The radius changes. What's the radius of our shell?
2 minus 1.
Yeah, 2 minus y. That's some y value. Okay, so we have 2 pi times r times h. That's the only difference is the radius. Any questions? I think that covers all of the scenarios. Sherpa, what question was it?
It was 7.3.
Number 3. So this one's different, I think, than the one you
Oh.
had, or is it this?
Mine
Is
was-
this the same?
Mine was the second edge, the derivative of second edge.
This one?
Yeah,
Yeah,
the same.
Oh, okay, cool, thank you. So this one, they say derive the following derivative formula, given these two things. The derivative of hyperbolic secant is negative secant tangent. And so they say first rewrite hyperbolic secant using hyperbolic cosine. So we'll. Just try to fit this in here. So the hyperbolic secant in terms of cosine is what?
1 over solution.
Yeah. So I don't have enough space. So we're taking the derivative of 1 over cosh. Okay. So I don't, that's what they asked next. I think that's all they want there. Use the information in the problem statement and the chain rule to calculate the derivative.
Which I found it was way easier to use the quotient rule.
Yeah, I think, yeah, for sure. So they're telling us to use the chain rule right now as we have it expressed. We would be using the quotient rule. So we're just going to rewrite that. Okay, so this is an inverse hyperbolic cosine. It's the reciprocal. So there is some room for confusion there. If it were the inverse hyperbolic cosine, the -1 would be here, and that's just that. This is the reciprocal though. Okay, so we're going to write it that way because it says use the chain rule. So we're going to take the derivative of the outside, leaving the inside alone, and then we take 1 away from the power. And then we multiply by the derivative of the inside. Well, I'll just write it out. I already have derivative. Okay. And so what we have is we've got our negative, I guess we'll leave this here, hyperbolic cosine to the -2 power times the hyperbolic sine. So that's negative hyperbolic sine over hyperbolic cosine squared. And then I think that's all they wanted us to show. It's negative secant, hyperbolic secant times hyperbolic tangent. So you just need to split that up. So there's negative hyperbolic tangent, there's hyperbolic secant. So maybe I should have just wrote it the other way, but whatever. So I don't know why they would specify to use the chain rule, because you could use the quotient rule as well. All the same. Yeah, so, if like a question's like this on the exam and it's kind of confusing, just please come ask me. Like, hey, what do you mean by this? I can totally clarify questions. Okay. Any other homework?
It's just kind of a dumb question, but is the inverse of the hyperbolic sine, would that be the hyperbolic arc sine?
Yeah.
Okay.
Yeah. Yeah, we don't look at those. I don't know why.
Would you do would it be abbreviated arc sine of h?
I think that's a common notation. Yeah, just like arc sine or
It's a
inverse.
lot of
sine.
letters for abbreviating a function.
Yeah.
physics problem in chapter 6.7 in the book. It had to do with lift. So a guy was on like a platform in the air, and he was lifting a chain up to the platform. We're supposed to calculate the amount of work that would take. Could we do an example of one of those?
Yeah, do you have one?
Yeah, there's one I don't have. There's one in the book. The main thing I was confused about with the water problems, when you're lifting the water out of the tank, you have to calculate the area of the cross sections of the water. Whereas with a chain, you would treat it as a one-dimensional object, so you wouldn't consider the cross sections. So
Right.
I guess my question is, why would you consider the area for the water problems, but not for the chain problems?
I don't know why they do that, to be honest.
Okay.
But they should have. Did they give you like a density for the chain?
They gave I believe they gave a density for the chain.
And it's going to be like 10 kilograms per meter, so it's going to be
Yeah.
a linear density.
Okay.
So yeah, in that case, you don't need to worry about area because you do just have a linear. But I'm not sure
Okay.
why they treat the chain as like a.
But with the water problems, it's a volume density, whereas
Yeah.
with this problem, it's just like a one-dimensional density.
Right.
Okay.
Right. Exactly.
Sounds good.
Yeah. So you would break up force as mass times mg. So you have mg as force, and then you break up mass as density times length.
Okay.
So you'd have density times length times gravity, and then your dy.
Okay. And
And
then
then
the
the-
water is density times area to get the mass.
Yeah, the
right?
length. The length is like so. Like the problem is like you have a person or a winch, and you have this. You have a chain. You know, let's say the chain is 30 meters. And the density of the chain is given.
I have a problem right here. Are you reading from that?
Yeah, it's the same
Oh, okay.
textbook.
Oh, okay, yeah. I was just saying.
So something like that. And they want to know, calculate the work required to lift the chain up. And so we're going to think of it that way. But the density kind of gives it away. Like this is a linear thing that we're dealing with. Force, we're going to think of as mass times gravity, which we're then going to break that up into density times length. Normally, like with an object, it's density times volume because it's an actual object. For whatever reason, they're treating this as like a linear thing, like the chain should have volume in theory, right? But this chain doesn't. I guess is the only way to say that. Okay, times dx. But this L right here is the distance of lift for your cross sections. So like this L isn't 30 because we're thinking about our cross section from that chain being right there, for instance. So how far do we have to lift that cross section versus this one versus this one versus this one, right? So that's what that L is going to correspond to. This is L. 30 minus y, I guess we'll call it. So for all of our cross sections, that's what L is. So density times our length times 9.8 times dy. Sorry, I should have, just to be concise, we'll do that. And then our bounds would go from where to where? 0 to 30.
Yes.
0 to 30. Right, because all of our cross sections, they start here, 0, and they're going to 30, or they're going from negative 30 to 0, however you situate that in the plane.
let's say in this problem, for some reason you were lifting the chain halfway up, so the bottom of the chain would be 15 feet. What would your limits of integration be for that scenario?
We're just gonna lift half of it.
Yes.
So then our limits of integration would go from 15 to 30, because we're just gonna lift this first half
Yes,
of.
the limits of integration for these kinds of problems should always be the area that you're lifting.
Right.
Okay.
Yes.
Because what's confusing about this is with the chain, you're lifting the bottom part too, so it seemed like you'd have to account for that in some way.
Right.
But only the top part you consider for that equation.
Yeah. Yeah.
Okay.
Yeah, and then so there's other examples. Perhaps we have a block attached to the bottom, but you can just calculate the work of the block without an integral.
Okay, you can treat it as like a point mass.
Exactly, point mass is all it is. Yeah. But we didn't. And I think, come to think of it, we had an example like this in our 6.7 notes that we did at work. So I won't ask a question like that on the exam. I'm sure you've had experiences of questions being asked that you never talked about. And if you haven't, get ready, because you will. You can go to the university, your instructor's gonna say, hey, we've got a test over chapter 3 tomorrow. See ya. That's kind of how that goes. So anyways, yeah, that's kind of the idea, linear density, linear kind of thing, which is not really
Okay.
accurate.
Okay.
Yeah. So yeah. Any other questions y'all have? That's all I have. Everybody ready then? Still have some studying to do?
I think I'm ready enough.
Ready as you'll ever be?
Ready enough, I guess. Good way to put it.
That's how it always works. Never feel totally ready. All right, well, I guess we'll call it a day. If anybody wants to hang out, I'll stay.